Photo of large atrium with windows and mirrors. Figure 10. One metaphoric architecture incorporates symbolic elements and patterns into the design to create narratives in a space, such as the windows in this government building that represent transparency. Computer science also uses patterns for solving problems and creating narratives. Credit, modification of Keep 'em Coming by Dylan/Flickr, CC by 20. Chapter outline. 10.1 Patterns Management. 10.2 Enterprise Architecture Management Frameworks. 10.3 Solution Architecture Management. TechWorks is facing many technical problems, such as difficulties in transferring the data between the divisions, sharing resources, and end-user training. The CIO suggested hiring a solutions architect manager who will be responsible for building teams, establishing relationships, setting strategy, and proposing solutions for the current problems, as well as finding any available opportunity. The first mission for the new solutions architect manager, Mr. John, is studying the current system design by setting up a meeting with the enterprise architects and the solution architects. Mr. John has asked the solution architects to finalize the design and implementation of the solution, and the enterprise architects to verify that the information technology strategy is aligned with the enterprise mission by analyzing the business strategy. Altogether, as a team, they created a plan for the solution by dividing the problem into subproblems using a divide-and-conquer approach. One, they reviewed the enterprise levels to verify proper bookkeeping of architectural knowledge, techniques, and artifacts, and their impact on architectural designs at various levels of scope. In the middle of the management process, Mr. John discovers that a data analyst and several software engineers need to join the team. The data analyst will define the required information for each level. The software engineers will leverage prior architectural knowledge at all levels of scope to create next-generation, secure, super-smart society, intelligent, and autonomous solutions. The team created many patterns to help address the problems, supported the creation of solutions, and put in place a framework ensures that enterprise solutions are in alignment with the evolving vision and strategy of the organizations that uses these solutions to operate and conduct day-to-day business. The main recommendation from the team to implement super smart society, intelligent, autonomous solutions is to adopt the Microsoft Azure Cloud Platform as a service and a target solution implementation framework to support customer-facing and internal business functions. Learning objectives. By the end of this section, you will be able to understand how to apply patterns at various levels of scope, organize patterns in hierarchies and leverage pattern catalogs and pattern languages. Relate to the current state of patterns management. A pattern documents a recurring problem and provides a reusable template in the form of a problem-solution pair within a given context. A pattern is not only a pairing of problem and solution, it provides the rationale that binds the problem and the solution together. Each pattern deals with a specific recurring problem in the design or implementation of a business solution. Patterns can be used to construct architectures at various levels of scope to guarantee specific properties. Patterns also capture existing, well-proven experience in solution development and help promote good design practice. Pattern hierarchy. Patterns range from abstract to concrete. Abstract patterns represent concepts without physical references, i.e., are not available to the senses. Concrete refers to objects that are available to the senses. For example, freedom is abstract, but the book on freedom is concrete. Design-centric patterns are organized in a pattern hierarchy that includes architectural styles, architectural patterns, and design patterns. An abstract pattern located at the top of the pattern hierarchy is called an architectural style. It captures a set of characteristics and features that make a structure identifiable. Styles are designed to capture knowledge of effective design for achieving specified goals within a particular context. An architectural pattern conforms to specific architectural styles and embodies architecture design decisions that are applicable to recurring design problems. They provide parameterized templates that can be adapted to provide solutions that are suitable to different development contexts. Design patterns conform to specific architectural patterns and provide granular design components to articulate them. Once a technology stack that picks specific technologies that should be used to implement the solution has been selected, design-centric patterns can be implemented. Each technology stack has a corresponding implementation-centric pattern hierarchy too that includes implementation styles, implementation patterns, and idioms. An idiom is a phrase or expression whose meaning cannot be inferred from the literal definitions of its individual words, but instead is understood through common usage within a language. Solution architects create several complex processes to successfully implement a business solution. These steps are: study the elements of technology that can be applied to solve a specific problem. Propose a combination of building blocks for the best possible fix to the problem. Design a solution and manage the implementation. After the solution architect finalizes the design and implementation of the solution, the enterprise architects verify that the information technology strategy is aligned with the enterprise mission by analyzing the business properties. Enterprise and solution architects use pattern hierarchies to create best practices for business and technical architectures that guide the implementation of solutions to business problems. Generalization and information hiding are used to keep more abstract patterns at the top of the hierarchy. The technology that allows the management of architecture results from decades of research in patterns management and frameworks used to plan and deliver solutions that meet business and technology strategies. Technology in everyday life. Patterns in everyday life. Patterns help us to organize our life activities. For example, using patterns, we can establish our daily activities using process patterns such as start my day and decompose this pattern into more specific process patterns such as waking up, eating breakfast, and getting ready for work. It is never the case that specific actions that correspond to these activity patterns occur the same way every day. How does the knowledge of patterns help people in everyday life? Provide a couple of illustrative scenarios to explain your opinion. Your scenarios should not be limited to integrating software patterns, but rather describe scenarios where people can refer to patterns to analyze real-life situations. Analysis and design model patterns. A blueprint is a high-level plan used in the development stage, and an enterprise architecture, EA, is a conceptual blueprint that defines the structure and operation of organizations. Design modeling provides a variety of different views of the system, like architecture plans for the enterprise. Examples of a design-centric architectural style are microservices. An example of a corresponding implementation-centric implementation style is REST services. When the problem appears, an architectural pattern embodies architectural design decisions that are applicable to a recurring design problem, parameterized to account for different solution development contexts. A design pattern relates to common design structures and practices that enable the creation of reusable software. An example of a design pattern is a singleton. A singleton restricts the instantiation of a class and ensures that only one instance of the class exists, e.g., a scoreboard object in a game should be derived from a singleton class to ensure that there is only one scoreboard object and one set of scores for the players at any given time. The enterprise architecture scope includes enterprise scope, higher-level patterns that can be applied to the overall structure of the enterprise. Solution scope, the pattern that can be applied to a single solution or system. Domain scope, the pattern that can be applied to a specific domain. A pattern hierarchy applies at all levels of scope, but variants of the higher-level patterns add additional embedded patterns that may be documented as a given enterprise architecture, EA model, which gets described more specifically at the portfolio or system levels. This is similar to the map of the city being part of the map of a region within the map of the world, as shown in Figure 10.2. Graphic of top-down systems, blueprints, scope. Enterprise portfolio, project system, subsystem, lots to little degree of generalization information, map analogy, scope, United States, State of Michigan, Wayne County, Detroit, Figure 10. 2. A blueprint shows top-down enterprise levels, enterprise, portfolio, system, and subsystem. Attribution, copyright Rice University, OpenStax under CC by 4. 0. License. Implementation patterns. In object-oriented programming languages such as Java, a singleton class can have only one object at a time. The purpose of a singleton class is to restrict the number of object creations to only one, which ensures access control to resources. A Java singleton class, Figure 10.3, is a corresponding implementation-centric example of an idiom that implements a singleton design pattern and allows one instance of a Java class to exist, as in Figure 10.4. Illustration of a singleton pattern demo. Figure 10.3. The singleton pattern demo class accesses the Java singleton class single object using the getInstance method to return the object. ShowMessage will print the message. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Screenshot of a Java singleton class. Figure 10. For a Java singleton class is a corresponding implementation-centric example of an idiom that implements a singleton design pattern and allows one instance of a Java class to exist. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Global issues in technology. Patterns of solutions. Problems and the need for solutions vary depending on the region of the world where people are located. For example, economically developing regions like Africa or parts of the Middle East do not have fiber optic networks as sophisticated as the ones deployed in Europe, where extensive investments in infrastructure have been made. This disparity impacts not only access to the internet, but also the potential for growth in education, technology, and healthcare systems. As a result, solutions to these problems are tailored to address the unique needs in these regions. Addressing these needs might involve developing alternative solutions like satellite internet or mobile broadband networks, which can provide connectivity. However, these solutions need to be cost-effective and scalable to ensure they meet the population's needs. Pattern catalogs. From a top-down standpoint, e.g., enterprise, portfolio, or project, architecture may appear in different levels of focus. The architecture areas span the whole enterprise and include various domains of architecture, such as business, information, application, and technology domains. The enterprise domains in the three standpoints are illustrated in Figure 10. 5. Chart displaying domains: business, data, application, technical, and scope, enterprise, portfolio, project. Abstraction level for enterprise technical is presentation, conceptual, logical, physical. Figure 10. 5. The architecture areas span across the whole enterprise and include various domains of architecture, such as business, information, application, and technology domains. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Patterns may be described using a pattern taxonomy and stored in a pattern repository or catalog. A pattern catalog is a collection of patterns that are organized according to specific characteristics and according to how the relationships between them are defined. Figure 10. 6 illustrates the general structure of a pattern catalog. A pattern catalog allows the bookkeeping of clusters of patterns at various levels of specialization, i.e., analysis and design model patterns versus implementation patterns. Illustration of a pattern catalog including solution development, implementation, analysis and design, and enterprise, business, information, application, technology. Figure 10.6 The general structure of a pattern catalog allows the bookkeeping of clusters. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. One example of a business architecture pattern that includes a generalization of business service composition and a pattern used to describe the sequencing of business services is business service orchestration. If the data does not include data presentation, then business service orchestration provides additional logic to process this kind of data. Another example of a business architecture pattern that focuses on the observed sequence of messages exchanged by peer services when performing a unit of work is called business service choreography. Figure 10.7 illustrates how various business architecture design patterns, e.g., exchange, shipment, order, and payment, may be combined via inheritance and composition to create a buyer-seller design pattern. Illustration of a business architecture design using inheritance and composition to connect exchange, shipment, payment, order, buyer-seller, and the components within. Figure 10. 7 various business architecture design patterns, such as exchange, shipment, order, and payment, are combined via inheritance and composition to create a buyer-seller design pattern. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. Link to learning. Read this article comparing orchestration and choreography to learn more about the advantages and disadvantages of both of them. Implementation patterns are typically specific to technology stacks that are selected as part of the specialization of a solution design, i.e., a transition from analysis and design model to implementation architecture. Figure 10. 8 illustrates how a pattern catalog is used to select the patterns and eventually create and deploy software engineering products at different project levels. Table with architecture and solution engineering views rows, analysis design, implementation, product deployment, and enterprise perspectives columns, business, information, application, technology. Figure 10. 8 A pattern catalog can be used to select the pattern based on the architecture and solution view for the enterprise perspectives. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license. Pattern languages. As we learned in Chapter 9 Software Engineering, a pattern language provides a connected view of how to apply one pattern in the presence of another. Concepts in practice. Are all pattern problems the same? Classifying software patterns is a similar problem to classifying patterns for buildings. For example, you would have to consider each room in a building and describe its role, e.g. kitchen, bedroom, along with specific related patterns, such as appliances, furniture, doors, and locks. As you may recall, design patterns are described using pattern templates. Enterprise pattern catalogs are more complex as they need to consider the degree of specialization of patterns. That is, whether they apply to the enterprise, portfolio, or project level. Therefore, there are many characteristics that must be considered when creating an enterprise pattern catalog, including the domain of applicability, scope, and level of abstraction. Current state of patterns management. A series of patterns that create an organization chart for developing software is called patterns management. In software engineering, the detailed study of engineering to design, develop, and maintain software, Christopher Alexander, a well-known building architect, is regarded as the father of the pattern language movement. Eric Gamma, Martin Fowler, and several other contributors are all part of the large community that has been focusing on collecting and documenting software patterns over the past 40 years. As a side note, the original wiki, the technology behind Wikipedia, resulted directly from Alexander's work, according to its creator, Ward Cunningham. Christopher Alexander's work has also influenced the development of Agile software development, which is an interactive approach to software development in order to deliver value to customers, and Scrum, which is a management framework that helps the development team organize the work to reach a specific goal. A framework is an implementation-specific skeletal subsystem for design work. A subsystem is a set of collaborating components that perform a given task included in software systems, and it is a separate entity within a software architecture. Enterprise architects use 4 architecture domains and architecture views to handle hybrid domains, e.g., an information systems architecture is as an architectural view that spans across the application and data architectures and handles both control and data flows. Therefore, the applicability of patterns may be qualified according to the combination of domain S of architecture they apply to business architecture patterns or information systems patterns. Industry spotlight. Patterns and the healthcare industry. Architectural styles and related pattern hierarchies are important in every industry today. For example, there are different styles of software architectures in healthcare that help address various types of business needs. These include mobile health architectures, emotion control management architectures, and remote surgery architectures. Mobile health architectures enable remote patient monitoring and ensure secure data exchange. Emotion control management systems track emotional patterns in patients. This allows for personalized mental health interventions. Real-time data and robotics allow surgeons to operate on patients who are located far away through remote surgery architecture. These architectural styles each play a critical role in enhancing healthcare delivery and operational efficacy. A more general view promotes the bookkeeping of architectures at various levels of abstraction as part of an architecture continuum, representing a structure composed of building blocks to reuse architecture assets that conform to a pattern language. The corresponding specializations are then organized in a solution architecture continuum. In this case, architectures used at the enterprise level in the industry and specific organizations are derived from foundation and common systems architectures, as shown in Figure 10. 9 and then realized practically as solution architectures. Architecture continuum, generic to specific, foundation architecture, common systems architectures, industry architectures, organization architectures. Solutions continuum, generic to specific, products and services, system solutions, industry solutions, organization solutions. Guides and supports with vertical arrows pointing in both directions in between, Figure 10. 9. The Open Group Architecture Framework, TOGAF, Foundation Architecture contacts common systems architectures, which contacts industry and organization architectures. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Learning objectives. By the end of this section, you will be able to understand how enterprise architecture management helps align business and technology strategies, explain what enterprise architecture frameworks are used for relate to the specifics of the TOGAF Enterprise Architecture Framework, build a strategic adoption roadmap, apply process frameworks and blueprinting templates in EAM enterprise architecture. EA is a comprehensive, well-defined approach to a business plan that utilizes information technology to meet the objectives of the business vision by aligning business and technology strategies. Information technology includes software, hardware, communication, data, and people. Managing EA will involve using Enterprise Architecture Management, EAM, which helps guide the adoption of technology stacks and corresponding implementation frameworks. EAM is the practice of managing an enterprise's business and IT architecture. It involves planning, designing, implementing, and governing the enterprise architecture to support the organization's goals. Enterprise architecture: there are many activities, business processes associated with an enterprise. However, its focus is on activities that allow it to meet current and future objectives. A business process is a series of steps a group of stakeholders performs to achieve an enterprise concrete goal or set of objectives. Current objectives reflect an enterprise's mission and short-term strategies, while future objectives reflect their vision and long-term strategies. To ensure successful development and execution of these strategies in either the short or long term, an enterprise will rely on EA as shown in Figure 10. 10. Chart detailing enterprise architecture, EA, current, future info and tech. Enterprise architecture, EA governance, defines roles, policies, processes. Enterprise architecture, EA management, EAM, uses agile methodology to implement and maintain. Figure 10. The goal of EAM is to provide enterprise capabilities to keep business solutions aligned with the enterprise strategy. Attribution: copyright Rice University, OpenStax, under CC by 4. 0 license. As illustrated in Figure 10.11, EA follows the requirements of a pre-established operating model, helps establish meaningful strategic boundaries, supports the management of core business capabilities that enable the development of a business platform for the execution of routine business tasks, and allows people to concentrate on improving the business rather than just purely running it. A foundation for execution is a combination of IT infrastructure, i.e., hardware, software, communication, and data, and digitized processes that automate the company's core business capabilities. The goal of the foundation for execution is to develop alignment between business and IT strategy. Creating and maintaining a foundation for execution relies on the company's operating model, strategy adoption roadmap, and a view of its reference architecture. A roadmap is used to guide an organization with planning and achieving business goals over time through technology. Designing foundation for execution. Strategic initiative establishes priorities. Foundation for execution, learning. Operating model defines standardization requirements for enterprise architecture, which defines core capabilities for foundation for execution and defines strategic initiative. Figure 10. 11. This figure depicts the EA foundation design for execution. Attribution: copyright Rice University, OpenStax, under CC by 40 license. Figure 10. 12 illustrates various operating models known as diversification, coordination, replication, and unification. These models correspond to variations in the way business processes are standardized and integrated. Table of business process integration: high, low, and business process standardization: low, high. High-low coordination, high-high unification, low-low diversification, low-high replication. Arrow rising from low-low up to high-high. Figure 10. 12 operating models known as diversification, coordination, replication, and unification correspond to the way business processes are standardized and integrated. Attribution: copyright Rice University, OpenStax, under CC by 40 license. The enterprise IT strategy is based on a collective set of principles. These principles form a consistent framework for technology decision-making and reflect a level of consensus among key stakeholder technology groups. The technology groups include senior leadership, the Architecture Council, and leading architects. Figure 10.13 shows the principles are intended to guide decision-making at all levels and are organized as a business, information, application, and infrastructure. Illustration depicting hierarchy of organizing framework. Technology delivery principles at top, followed by enterprise architecture principles, architecture design principles, business, information, application, technical infrastructure, also listed. Information security principles and IT governance principles. Figure 10.13. The organizing framework includes information security principles, technology delivery principles, enterprise architecture principles, and architectural design principles. Attribution, copyright Rice University, OpenStax, under CC by 40 license, Figure 10. 14 summarizes typical enterprise capabilities within various business units such as manufacturing, corporate, and technology. List of capabilities for client dreams, planning, tracking, advisor acquisition, financial practice management, distributor market private, field management, admin distributor, manufacturing assets, products, accounts, distribution, product distribution, corporate, capital, finance, legal, technology, solution, planning, building, execution. Figure 10, 14 typical enterprise capabilities within various business units such as manufacturing, corporate, and technology are shown. Attribution, copyright Rice University, OpenStax, under CC by 4. 0 license investment in technology may have possible impacts, such as goals, desired expectations, and metrics. In the goals, we estimate many factors, such as the required time, the deliverables information, the cost of quality, and the outputs. In the desired expectation, we evaluate the project, e.g., right project, right cost, right timing, and right resources. In the metrics, we measure the investment demand, employee satisfaction, and quality of service, i.e., availability and cost. Figure 10. 15 illustrates the possible impact of investment initiatives in technology capabilities as they are arranged in the Plan and Solutions section, built into the Solutions section, and deployed into products delivered to customers. The process will start with planning solutions and investments, then building solutions, and finally running solutions. Chart of activities, plan solution and investments, build solutions, run solutions for goals, desired expectations, metrics. Figure 10, 15. There are many possible impacts of investment initiatives in technology capabilities. Each section lists the assigned capabilities and/or impacts. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Business and technology executives are responsible for ensuring that an IT project achieves division-wide and company-wide objectives by engaging with the enterprise architects. EA is an evolving practice that takes time, investment, and patience. It should provide a strategic framework for organizations to handle technological disruptions by aligning IT systems with business goals, while helping decision-makers implement changes that drive innovation, resilience, and efficiency to ensure short-term initiatives and long-term projects can contribute to the success of the company. A leading healthcare organization aimed to reduce operational costs while streamlining patient care. They used EAs to identify the need for a unified data system. The system needed to integrate patient records, billing, and telemedicine services. The EA team presented recommendations, including adopting cloud-based platforms and automated workflows. This helped the organization handle business disruptions, minimize data silos, and improve service delivery. The project aligned with division-wide objectives, showcasing how EA practices can drive strategic transformation in response to industry challenges. Aligning business and technology strategies. Aligning business and technology strategies is typically difficult on an ongoing basis because of the lack of alignment with enterprise-driven initiatives. Enterprise architecture helps align business and technology strategies, as illustrated in Figure 10. 16. This alignment is a continuous process and is achieved through the business IT alignment lifecycle. Graph of time and maturity. Baseline standard goes up with plan, do, check, act cycle occurring along with continuous quality improvement to end at business IT alignment. Figure 10. 16. The business IT alignment lifecycle is a continuous improvement process that helps align business and technology strategies. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license. The business IT alignment lifecycle helps organizations align their business goals with IT strategies through different stages. The first stage is initiation, which involves checking the problem facing the enterprise or available opportunities. The second stage is strategy, which involves designing solutions. The third stage is planning, which involves planning how to implement the solution. The fourth stage is execution, and it involves implementing the solution. The last stage is assessment, which entails evaluating the solution. The enterprise team should be careful when developing business IT alignment because enterprise business solutions may lack alignment with the enterprise-driven initiative. In other words, business solutions should take into account the architectural guidelines that are set forth at the enterprise level and not just reinvent the wheel. Figure 10. 17 shows the 4 symptoms that may lead to the lack of alignment. Lack alignment with enterprise-driven initiatives. Vision strategy not aligned with enterprise strategic goals. Business solution development not delivered on time budget. Poor quality. business solution, refactoring difficult to evolve, business solution, maintenance hard to maintain. Figure 10:17 when the four symptoms do not overlap, enterprise business solutions lack alignment with enterprise-driven initiatives. Attribution, copyright Rice University, OpenStax, under CC by 4. Zero license, the first symptom appears when the created solution is not aligned with the enterprise goal. The second one appears when the business solutions are not delivered on time and on budget, or if the outcome doesn't reach the expected quality. The third one appears when it's difficult to maintain the system or the solution. The fourth symptom appears when it's hard to evolve the business solutions. Global issues in technology, EAM across the globe. All the EAF frameworks in existence were developed in the United States and Europe. The most widely recognized EAFs are TOGAF, the Open Group Architecture Framework, and the Zachman Framework. EAFs are not typically designed to be adaptable to different organizational contexts and different cultures. Therefore, there is uncertainty about how effective these frameworks are in diverse cultural contexts, such as in Asia and Africa, where decision-making processes and organizational structures may differ from those in the United States and Europe. In addition to the alignment, enterprise architecture management uses enablers to provide enterprise capabilities to keep business solutions aligned with the enterprise strategy. An enabler supports the activities needed to extend the architectural runway to provide future business functionality. Figure 10:18 shows 5 different kinds of enablers, which are listed in Table 10. 1. Enablers. 1. Best practice process. 2. Best practices knowledge base. 3. Extensible framework for traceable/reusable artifact. 4. Design and runtime tools. 5. Incremental iterative enterprise. 4. 5. Provide necessary supports for 1. Figure 10:18 Enterprise Architecture Management provides enterprise capabilities, known as enablers, to keep business solutions aligned with the enterprise strategy. Attribution. Copyright Rice University, OpenStax, under CC by 4. Zero license, type description, best practice process patterns, artifact types, and organization models subsume specific organization and location models within the enterprise, along with process patterns and artifact types to guide the implementation of business solutions. Best practice knowledge base extensible methodology based on business solution patterns and extensible knowledge foundation. Best practices for ongoing strategies and business solution development, extensible framework for reusable artifact types and methodology, selects subsets of process patterns and artifact types. Customizes implementation of process patterns that fit the enterprise environment, and leverages existing enterprise approaches. Design and runtime tools provide necessary support for Enabler 1, selects best practice processes, approach tools, and artifacts to help implement reference architectures. Incremental iterative enterprise transformation methodology suggests the use of an incremental iterative, CMMI compliant, enterprise transformation methodology that improves the maturity of the enterprise, or its ability to keep business and it aligned over time, as illustrated in Figure 10:19 Table 10:1 Types of enablers chart of EAM awareness desire knowledge ability reinforcement change management methodology. Figure 10:19 This figure shows how the generic EAM awareness desire knowledge ability reinforcement change management methodology applies in the context of a business pattern-driven modeling process pattern. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Think it through. Aligning strategies. Aligning business and technology strategies involves ensuring that goals and objectives of business and technology are supportive. How is it possible to align business and technology strategies? Enterprise Architecture Frameworks EAM is a management practice that establishes, maintains, and uses a coherent set of guidelines, architecture principles, and governance regimes that provide direction and practical help in the design and development of an enterprise's architecture to achieve its vision and strategy. EAM brings the highly distributed knowledge of all experts to the table and allows every participant to provide such knowledge and input in terms that best fit the experience and expectations of the contributing stakeholders. Industry Spotlight. EAM in healthcare. EAM is important in every industry today. It plays a vital role in healthcare to handle unexpected challenges, such as those seen during the COVID-19 pandemic. By providing a framework that aligned business and IT strategies, EAM allowed hospitals and other medical organizations to quickly adapt to the crisis. EAM was used to manage supply chain disruptions, scale telemedicine services, and rapidly build respirators to ensure that healthcare infrastructures were agile, resilient, and capable of maintaining high-quality care in the face of surprises. As EA and EAM regard the enterprise as a large and complex system, or system of systems 3, it is necessary to manage the scale and complexity of this system. To address this requirement, an Enterprise Architecture Framework, EAF, provides tools and approaches that ensure that enterprise solutions are in alignment with the evolving vision and strategy of the organizations that use these solutions to operate and conduct day-to-day business. EAFs provide structured guidance that is divided into three main areas: descriptions of architecture, how to document the enterprise as a system, methods for designing architecture, overarching enterprise architecture process, composed of phases and broken into lower-level processes, composed of finer-grained activities, organization of architects, guidance on the team structure and the governance of the team, including the skills, experience, and training needed to describe architectures. EAFs employ flexible data models built upon meta-models that provide evolving outlines for capabilities and relationships. At a high level, EAFs provide foundational principles, an organizing framework, a comprehensive and consistent method, and a set of governing processes and structures, as illustrated in Figure 10.20. Illustration of reference architecture: principles, framework, business, application, technical, people, process, information, method, plan, deliver, operate, governance. Figure 10.20. This high-level view of EAF reference architecture shows the main components: principles, framework, method, and governance. Attribution: copyright Rice University, OpenStax under CC by 4. 0 license. The reference architecture is built upon principles. A principle forms the foundational rules that guide its design and implementation. The reference architecture uses architectural terms as well as numerous principles, policies, and guidelines to govern the architecture. The framework serves as the organizing structure and outlines architectural domains and disciplines to ensure separation of concerns and alignment between business goals and it. The method consists of defined, repeatable processes that ensure a consistent and controlled execution of the reference architecture. The processes and organizational structures that ensure adherence to the reference architecture are considered governance. Technology in everyday life: EAMs and EAFs in real life. EAMs are found in common technologies and are used to ensure systems operate smoothly as user needs change. For example, home automation systems are often expanded, with the user requiring the ability to add new devices, such as a smart refrigerator or thermostat. However, the system needs to maintain compatibility with the existing devices it is connected to. EAFs provide structured guidelines to manage these changes, ensuring flexibility and scalability. How can EAMs ensure seamless integration of new smart devices into your home system? How do EAFs help maintain flexibility in personal technology ecosystems? As the practice of EA evolves, the supporting EAF frameworks that enable communities and enterprises to apply EA also evolve. Indeed, as solution complexity increases, the ingenuity needed to master it must continuously improve. In fact, architecture strategies keep playing an enormous and ever-increasing role in determining whether an enterprise is successful. The next generation of EAFs is focused on enabling the creation of dynamic ecosystems and related architectures that provide value for all business participants via systems of insight that integrate and facilitate decisions across systems of record, i.e., focus on costs, systems of operations automation, i.e., focus on operational expense OPEX, systems of design, i.e., focus on innovation, and systems of engagement, i.e., focus on customer experience. Figure 10.21 shows the evolution of EA frameworks that has taken place over the years. Graph: IT evolution, mainframe, PC, internet, smart computing, IT evolution, and IT business drivers, asset optimization, business process flow, individual productivity, automatic transaction processing, and EA drivers. It fuels innovation, complexity, distribution, costs. Figure 10.21. This chart shows the relationship representation of IT business drivers and IT evolution over time. The evolution ranges from the mainframe to smart computing. The next generation EA framework will optimize human, physical, and environmental assets. Attribution: copyright Rice University, OpenStax under CC by 4. 0 license. The architecture subsumed by this new breed of ecosystems is illustrated in Figure 10.22. It relies on various layers that can be modeled using next-generation EAFs as follows. Trust models ensure that all participants within the ecosystem share and agree on additional values, rather than just operate only for financial profits, e.g. respect privacy, guarantee security, provide customer-oriented value and social values, improve the level of quality, as well as shared outcomes, including externalities such as pollution or regulation. Business models ensure that the values identified in trust models are shared, and business models can be established that split the margin and revenue between ecosystem participants. Orchestration models optimize the split of responsibilities and orchestrate services to deliver the best values for customers at the right price quality, e.g. the Links Navigation Digital Experience Journey or the Knowledge Flows Journey maps to services and processes at the ecosystem level. Shared services models include supporting data and application services. Business networks enable the sharing of processes and data. For example, cloud applications shared between partners in digital business networks via a mix of shared and multi-tenancy architectures. Table illustrating integration. Trust models, business models, orchestration models, shared services, business networks. Orchestration affects shared services and trust models. Business models affect trust models. Figure 10. 22. Using next-generation EAFs, various layers can be modeled as trust models, business models, orchestration models, shared services models, and business networks. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. To provide adequate support, next-generation EAFs must supply an extensive set of generic capabilities as part of an underlying meta-framework. A meta-framework describes the framework in more detail, as illustrated in Figure 10. 23. Clearly, these capabilities go beyond modeling and related features and must be spanned across EAF requirements for IT automation, IT governance, and IT context management. IT automation is the process of creating systems to reduce manual intervention. IT governance is the process that ensures the effective and efficient use of IT in enabling an organization to achieve its goals. IT context management is a dynamic IT process that uses data in one application to point to data resident in a separate application. Chart. IT automation, change management, cost impact analysis, data lineage modeling, connectors, IT governance, risk management, data transparency, data aggregation, IT context, applications, semantic layering, business taxonomies, scoring, search, versioning, metadata repository. Figure 10, 23 EAF requirements for IT automation, IT governance, and IT context management are shown. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. There are many examples of EAFs, such as TOGAF, Gartner Enterprise Architecture, C4ISR, CORBA, Federal Enterprise Architecture, Zachman Framework, and many more. Each one of the EAFs follows a specific format and uses a different specification. Table 10. 2 shows examples of EAFs and their specifications. Enterprise Architecture Framework Specifications, TOGAF, the most popular EAF today. 4 uses the Architecture Development Method, ADM, with 4 interlinked domains, business, application, data, technology, and provides a set of views for each domain. Gartner Enterprise Architecture identifies and analyzes the execution of change toward desired business vision and outcomes. C4ISR, command, control. Computers, communications, intelligence, surveillance, and reconnaissance replaced Technical Architecture Framework for Information Management. It was renamed as DODAF in 2003, has minimal focus on methodology, unlike ADM focuses on operational system. In technical views, CORBA, Common Object Request Broker Architecture, Object Request Broker, Based Architecture, Application Architecture, Enterprise Architecture Planning Method for planning development of business data. Applications. In technology analogous to TOGAF, but does not have TRM and SIB. Federal Enterprise Architecture, Practical Guide End-to-End Process to Manage Enterprise Architecture, aligned to TOGAF Lifecycle. Federal Enterprise Architecture Framework, provides guidance on structuring enterprise architecture, organizes architecture into 5 reference models to provide a standard methodology analogous. TOGAF, views ISO IEC TR 14252, IAEA STD 1003. 0. Withdrawn. TOGAF is more detailed ISO RMODP formal description techniques for architecture specifications, distributed process, and heterogeneous environments. Spirit Platform Blueprint, referenced within TOGAF Technical Architecture Framework for Information Management basis, on which TOGAF is built. Zachman Framework, more detailed than TOGAF in capturing viewpoints and views. which can be filled in using ADM. Does not specify any method security and manageability, are not explicitly specified in Zachman 5 Table 10. 2. Enterprise Architecture Frameworks and Specifications. The Open Group Architecture Framework. The Open Group Architecture Framework, TOGAF, is an EA methodology and framework used by leading organizations to improve business efficiency. TOGAF focuses on elements of consistent methods, standards, and communication. TOGAF enables organizations to pursue a systematic approach toward the development process in order to reduce errors, manage timelines, stay within plan budget and scope elements, and have efficient processes to produce quality results. TOGAF helps practitioners avoid being locked into proprietary methods, utilize resources more efficiently and effectively, and realize a greater return on investment. In 1995, the original development of TOGAF version 1 was published as a reference model for enterprise architecture, offering understanding into the U.S. Defense departments (DoD) own technical infrastructure, including how it's structured, maintained, and configured to align with specific requirements, Figure 1024. As of today, the TOGAF is a detailed method and a set of supporting tools for developing an enterprise architecture. It may be used freely by any organization desiring to develop an enterprise architecture for use within that organization. Timeline: 1995, TOGAF first published, 2002, TOGAF 7 Technical Edition, 2003, TOGAF 8 Enterprise Edition, 2006, TOGAF 811, 2011, TOGAF 9. 2018, TOGAF 9.1 Figure 10. 24. This timeline shows the development of TOGAF over time. The first version was in 1995, and the most recent version was in 2018. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. TOGAF is the widely used framework to establish and define enterprise architecture. It presents an approach to planning, designing, implementing, and governing the enterprise-level information technology architecture of the organization. It mainly focuses on 4 modular structures, which include application, business, technology, and data. The main purpose of defining the TOGAF framework was to have an architectural model that can be replicated with few errors in each progressing phase. Establishing a common language and understandability mechanism bridges the gap between IT and the business by bringing clarity to the information, establishing methodology, and having practical implementation guides. The TOGAF standard includes the Architecture Development Method, ADM, which is a detailed step-by-step process for developing or changing an enterprise architecture. It also allows for changing a content framework to help drive greater consistency in the outputs that are created when using the ADM Figure 10.25. The TOGAF content framework provides a detailed model of architectural work products. Common system architectures are used by many enterprises. Industry architectures are industry-specific, while organizational architectures are company-specific. Enterprise continuum shown with Architecture Development Method, ADM, on arrow from left to right, foundation architectures, common system architectures, industry architectures, organizational architectures, Figure 10.25. The most generic component of the continuum is the foundation architecture, which is usable by any IT organization. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Link to learning. ADM defines the TOGAF approach for establishing processes linked with enterprise architecture. It provides a recursive and tested process development business architecture. Every phase of the ADM is iterative in nature to develop an enterprise-wide architecture. The ADM can be adapted and customized to a specific organizational need to help inform the business's approach to information architecture. ADM helps businesses develop processes that involve multiple checkpoints and firmly establish requirements to repeat the process with minimal errors. The categories of patterns are specification patterns, vision patterns, process patterns, governance patterns, migration patterns, usability patterns, information patterns, business patterns, and interoperability patterns. The phases suggested by the ADM are as follows. Preliminary phase. This phase defines enterprise principles, IT principles, and architecture principles, i.e., how do we do architecture. It is not considered a part of the ADM cycle, as it may be revisited at any point throughout the cycle. This phase involves the organization and governance of the architecture, its general principles, methods, tools, and the architecture repository, and is the jumping-off point during which an organization starts an ADM cycle. The outputs of this phase are framework definition, architecture principles, and reference to an organization's principles and goals. Phase A, architecture vision. This is the first phase of the ADM cycle and begins with the receipt of a request for architecture work within a sponsoring organization. During this phase, an organization establishes the project, identifies business goals, reviews architecture and business principles, defines the scope and constraints of an architecture effort based on an assessment of resource and competence availability, and identifies stakeholders and business requirements. A vision is developed regarding the project's organization, orientation, roadmap, baseline architecture, and risks. In the end, a business has a document statement of architecture work to submit for approval. Phase A is where the organization answers the questions of where we are going, how we are getting there, and with whom. Phase B, business architecture. During this phase, an organization describes the baseline business architecture that currently exists and the target business architecture that they will work to implement. The next step is creating business architecture models, organization structure, business goals and objectives, business functions, business services, business processes, business rules, correlation of organization and function, and trade-off analysis reports. To accomplish this, gap analysis and modeling must be performed for and between the baseline and target business architectures. The gap analysis includes people, processes, tools, information, measurement, financial, and facilities. Such modeling may include a variety of tools, including activity models, use case models, class models, node connectivity diagrams, and information exchange matrices. Figure 10. 26 illustrates common activities among several phases. Some of TOGAF phases describe baseline architecture, describe target architecture, measure gaps, evaluate impact, draft the roadmap. Figure 10. 26 phases B, C, and D of TOGAF AMD represent multiple activities that include describing the baseline architecture, describing the target architecture, measuring gaps, evaluating impact, and drafting the roadmap. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Phase C, Information System Architecture. Information System Architecture is composed of data architecture and application architecture subphases. The design framework that structures how data is collected, stored, managed, and utilized within a system is called data architecture. The patterns used to design and implement an application are considered its application architecture. The objective of this phase is to develop target architectures covering either or both subphases, depending on the project scope. The business processes supported in this phase are those that are supported by it, as well as the interfaces of those processes with non-it-related processes. Data architecture reviews and selects principles, reference models, viewpoints, and tools. It creates data architecture models for each viewpoint, such as the C4 ISR architecture framework and conceptual data model map to business architecture. Then it performs trade-off analysis, completeness, and conformance. After that, it selects data architecture building blocks, conducts checkpoint review of the architecture model, reviews qualitative criteria, completes the data architecture, conducts checkpoint impact analysis, performs gap analysis, and creates reports. Application architecture subphases develop a baseline applications architecture description, review and validate application principles by selecting reference models, viewpoints, and tools. Create architecture models for each viewpoint. Identify candidate applications, i.e., business architecture and data architecture. Conduct checkpoint review, review the qualitative criteria. Complete the application's architecture, perform gap analysis, and create report. Phase D, Technology Architecture. The purpose of this phase is to develop a technology architecture that defines the platforms and execution environments on which the organization's applications run and the data sources are hosted. The key steps involved in this phase are: develop the baseline technology architecture description to the extent required to support the target technology architecture. Develop the target technology architecture by considering different architecture reference models, viewpoints, and tools. Then, create an architecture model of building blocks, select the services portfolio required per building block, confirm that business goals and objectives are met, choose the criteria for specification selection, complete the architecture definition, and conduct gap analysis. Phase E, Opportunities and Solutions. Phase E identifies the key business drivers, the change parameters, the major phases required, and the projects that are undertaken to move the organization to the target environment. Phase E reviews gap analysis, i.e., studying the gap between the current system and the future system, performs architecture assessment, and identifies software packages for projects. This phase also involves the study of the technical, organizational, and financial requirements and constraints of the project. Phase F, migration planning. During this phase, the various projects required to implement the architecture are sorted into priority order based on dependencies and the cost-benefit assessment of the various projects. Migration schedules, i.e., outline the timeline, tasks, and resources needed. Risk assessment, i.e., identifying and analyzing potential risks. Project goals, i.e., defines the goals and outcomes. Project constitutions, i.e., outlines the main principles of the system. Implementation roadmap, i.e., steps to follow in the implementation, and project organizations are established. Phase G, implementation governance. This phase establishes the final version of architecture contracts that govern the overall implementation and deployment process and involves developing recommendations for each implementation project. Implementation governance functions to ensure implementation projects conform to the defined target architecture. The steps in this phase are: formulate project recommendations, document architecture contract, establish architecture compliance review process. Phase H, architecture change management. This phase establishes the process through which the deployment of the architecture is managed. Architecture change management provides for continuous monitoring of factors that may affect the implementation process, such as change requests, new developments in technology, or changes to the business environment. Such factors may trigger new ADM cycles as the project evolves. The steps involved are: monitor technology changes, monitor business changes, assess changes, hold architecture board meetings, link to learning. The TOGAF content framework contains vision, requirements, business architecture, information system architecture, technology, and architecture realization. You can learn more about it by exploring the content framework and enterprise meta model in the Open Group's official guide. This framework provides an essential structure for managing and aligning IT strategies with business goals. TOGAF's foundation architecture sets forth the following: architecture building blocks and standards, generic services and functions to build specific services, technical reference model, standards information base. TOGAF also provides an enterprise continuum that addresses the architecture continuum and the solution continuum, and an architecture governance with guidelines relating to the following: management and control of architecture works at an enterprise level, repositories, process flow control, architecture board, including architecture compliance and contracts, process and content details, table 10. 3. Process content, environment management, regulatory requirement, assessment selection of models, architectures, technologies, and product service level agreements, SLAs, and online licensure application systems, OLAs, dispensation authority structures, policy management, organizational standards, and architectures, retirement of assets technology/product set. Table 10. 3. Process and content details of architecture governance. Concepts in practice. EIM faces new challenges. The business of evolving solutions to constantly adapt to change is akin to what people face in real life as they react to change when facing unforeseen situations. This happened recently because of the COVID-19 pandemic. It is not always possible to rely on the current state of a solution and its ability to evolve. Sometimes a leap forward must be made, and it is more important to manage the need to evolve rather than try to adapt an existing and perhaps obsolete solution. While it differs from traditional EA techniques, EAM provides a management practice that establishes, maintains, and uses a coherent set of guidelines, architecture principles, and governance regimes that provide direction and practical help in the design and development of an enterprise's architecture to achieve its vision and strategy. As a result, EAM allows leaps forward to face unexpected changes, such as having to innovate to remain competitive, rather than simply focusing on being the best at providing a given service. Strategic Adoption Roadmap. EA is typically used by companies to produce a blueprint of the future state and a roadmap for getting there. Companies' shift to lean and flexible operating models directly affects how their IT workforce architects design future business solutions, wherein it needs to enable the new operating model by advancing business capabilities through efficiently integrated and standardized business processes and corresponding solutions. EA ensures the alignment of business architectures with solution architectures by providing a holistic view that links all architecture domains through an enterprise reference architecture, ERA. The result of this work, which is produced through an integrated planning process and methodology, aligns and sequences IT investments to optimally achieve the company's strategies. The assembly of the roadmap draws upon three distinct architectural domains: business architecture, business solutions architecture, IT solutions architecture. The adoption roadmap results from implementation planning, as illustrated in Step 8 of Figure 10. 27. Creating a roadmap requires a current state assessment, future state definition, and gap analysis. Roadmap current state assessment: 1. Business inventory, 2. System inventory, 3. Business IT alignment, future state definition, 4. Establish priorities, 5. Business architecture, 6. Technology architecture, implementation roadmap, 7. Solution options, 8. Implementation planning. Figure 10.27. These are the steps of adopting a roadmap. The first step is current state assessment, followed by future state definition, and the last step is roadmap implementation. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Creating a future state model definition requires an understanding of future state needs and the definition of a target strategy based on various business and IT drivers, as illustrated in Figure 10. 28. Illustration. Information sources, future state needs, future stage operating strategies, capabilities, quality of service, key business drivers, IT enablers, solutions, future state models. Architecture modeling best practices, future state models. Figure 10. 28. Business and IT drivers define the future state need and how it will be validated by individuals and stakeholders. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Developing business drivers requires an evaluation of the dynamics of change that are necessary to keep sustaining the business. Businesses often use the 5 Porter forces illustrated in Figure 10.29 to analyze business dynamics. To ensure that a product competes in the market, you should study these factors. Is there any barrier to entering the market? Are there any competitors competing with your product's price? Is there any threat of substitute products? What is the buyer and supplier power? 5 Porter forces: entry barriers, large operations, new regulations, strong network, internal rivalry, competition on price term service, threats of substitutes, highly commoditized product, supplier power, agents, vendors, outsourcing, and buyer power. Figure 10.29. Analyzing business dynamics using the 5 Porter forces: entry barriers, internal rivalry, threats of substitutions, supplier power, and buyer power. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Enterprise business and technical architectures. A reference architecture diagram may be used to create a view of a company's enterprise architecture. For example, fictional airlines opted for a unification operating model, and its reference architecture is depicted in Figure 10.30. In the current competitive environment, airlines concentrates on products and services through the value chain to increase customer satisfaction and the company's profit. Airlines enterprise architecture chart with back and forth arrows. Operational activities: departure, arrival, monitor, unload, upload. Airline system: flight, ticket, customer, employee, aircraft, partner, customer experience, tickets, coupon, points, boarding, baggage. Figure 10.30. Airlines enterprise architecture includes the customer experience pipeline to support the airline system with events and to create relationships between the records. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 10.31 illustrates how various business and enterprise technical architecture assets may be represented. The technical architecture is divided into 3 layers: future state business capabilities models, e.g., management liability, claims, finance, and MIS stakeholders, business needs for the next 3 to 5 years, and the technology architecture model to support the evolving business needs with respect to best practices and strategic IT goals. Future state business capabilities layers: underwriting, policy servicing, claims processing, finance accounting, business needs, value chain analysis, operating strategies, business drivers, IT enablers, business architecture framework, technology architecture model, drill down key implementation patterns. Figure 10.31. The technical architecture is divided into three layers: future state business capabilities models, business needs, and the technology architecture model. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. These assets are architectural drawings, referred to as blueprints, and are stored in an asset catalog according to their domains and levels of abstraction. Different UML models and blueprints provide high-level architectural details meant to help visualize the big picture. Figure 10.32 shows different levels of abstraction, including conceptual, logical, and physical. Architecture domain table, application architecture column, enterprise row, level of abstraction, conceptual, logical, physical, data architecture application architecture column, portfolio domain row. Level of abstraction, physical. Figure 10.32, focusing more on an application domain in the enterprise, provides more details about the level of abstraction. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Enterprise architecture process frameworks and related patterns. Various process patterns may be applied to create enterprise architecture assets. EAFs such as TOGAF implement specific processes and provide patterns and templates that may be followed to derive enterprise architecture assets. TOGAF provides an architecture metamodel that allows content adaptations in order to meet specific enterprise requirements. A metamodel provides evolving outlines for capabilities and relationships. Figure 10.33 illustrates a business architecture blueprint. The blueprint represents client focus, risk and financial management, business management and support based on product and sales and/or service. Model showing client focus, client and channel management, product, sales, service, risk and financial management, business management and support, information technology, etc. Figure 10.33 business management focuses on the client and manages the risk for products, sales, and services. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 10.34 illustrates a sample application information system architecture blueprint. The blueprint represents participants, interaction through electronic business gateways, processes, services, components, data about all of the components, rules, and technical services. Illustration of an information system: participant, interaction, processes, services, components, data, vendor, integration, technical services, rules along with examples. Figure 10.34. This sample representation of the blueprint for an information system shows all of the components and how they relate to each other. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 10.35 illustrates a sample information architecture blueprint. The blueprint shows the relationships among transactional data stores, e.g., database that keeps track of daily transactions for one store, operational data store, e.g., database that keeps track of daily transactions for all stores, data warehouse, e.g., data management system that facilitates analytics and business intelligence queries at the enterprise level, and data marts, e.g., data management system that facilitates analytics and business intelligence queries at a business unit or department level. After running the data bus, the reporting and analysis step starts to produce operational reports, management reports, analytic reports, and e-commerce files. The blueprint for enterprise architecture helps align business and IT strategy, as well as provides a clear vision on how technology supports the enterprise goals. In addition, it's a main reference tool to coordinate the collaboration between the different enterprise components: information architecture blueprint, transactional data stores, business data stores, enterprise, operational data stores, data warehouse, reporting and analysis, integration, technical services. Figure 10.35. This sample representation of the blueprint for information architecture shows the relationships among the components. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 10.36 illustrates a sample technology infrastructure architecture blueprint. This blueprint shows three different types of clients: browser client that is using the browser to access the internet web service, pervasive client that is using public-private network to access the gateway, partner service with a database that uses a public-private network to access the gateway. In addition, the blueprint represents the interaction and security level for each user to access the integration application and data bus. Technology infrastructure architecture blueprint: internet and public or private network to Internet Web Server or Gateway, to Integration Application and Data Bus. Figure 10. 36. This design shows a sample representation of the technology infrastructure architecture blueprint. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. ArchDevSecOps. DevOps describes an approach to improving collaboration between the development and operation of services. DevOps is a blend of the terms development and operation. ArchDev is an example of an accelerated architecture-driven digital transformation process, which helps companies proactively embed stakeholder interest and sustainability into the company's digital growth. Agile EA Management, AEAM, is a methodology used for software development and project management. AEAM uses divide and conquer methodology by breaking individual projects into smaller pieces to make them easier to manage, which speeds up design processes and produces quality products. ArchDev is enabled by methodology, tooling, and IP. It incorporates AEAM and is compatible with TOGAF to assess as-is and to-be states and a gap analysis to identify transformation initiatives that feed into the portfolio management process. The business context driving prioritization is a major factor in selecting appropriate architectures for initiatives. Where DevOps integrates the tasks required to accelerate the development to deployment cycle, ArchDevSecOps integrates the disciplines required to identify a target architecture, which informs the solution design, monitors its implementation, and ensures its continued validity in the face of a changing environment. If changes in requirements or business context necessitate architecture revisions at any point in the development cycle or thereafter, ArchDevSecOps processes facilitate identifying the best replacement and following the most efficient path to migrating to it. ArchDevSecOps, therefore, enables businesses to strike a balance between expedience and architecting business, which allows preserving business agility and sustainability. Blueprinting templates. An enterprise architecture blueprint is a visualization of the architecture at the conceptual, logical, and physical level of an enterprise, showing concepts, their elements, and the components that implement the elements and their interrelationships. Various blueprinting templates are available to help derive architecture diagrams. Figure 10.37 illustrates a template that may be used to create conceptual business architectures. The diagram shows how the template may be applied in an insurance industry context. The diagram represents the enterprise value chain, which includes sales and marketing, product development, underwriting, finance and accounting, servicing, and claim processing. The blueprint includes many components and services, such as BPM processes, business capabilities, and business services. Value chain business capabilities will differ per value chain chart. Sales, marketing, product development, underwriting, finance, accounting, servicing, claim processing to business users, events, channels, BPM processes, process metrics, BRM rules, business services entities. Figure 10.37 The diagram represents the enterprise value chain, which includes sales and marketing, product development, underwriting, finance and accounting, servicing, and claim processing. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. To specify the conceptual business architecture of the underwriting value chain element, Figure 10.38 drills down into the underwriting value chain element. Illustration of value chain to underwriting with new business and fulfillment. Figure 10.38 Underwriting is an element of the value chain and incorporates new business and fulfillment. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Representing the logical architecture models using a blueprint template is different. Figure 10.39 illustrates a blueprint for the logical architecture model, shows the separation of concerns through layering, and enables high cohesion and low coupling across the application component. This blueprint represents interaction integration, bus process integration, application integration, service integration, data integration, and infrastructure integration. Using this template helps to create a detailed logical architecture model that may then be split into separate layers to convey more readable details. Chart of interaction integration, business process integration, application integration, service integration, data integration, and infrastructure integration. Figure 10.39 This blueprint represents interaction integration, business process integration, application integration, service integration, data integration, and infrastructure integration. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Architectural and implementation styles. As you may recall, the specification of architectures starts at a high level within the enterprise to help align business and IT strategy. The main strategies are typically to achieve operational excellence as well as competitiveness. Figure 10:40 represents the relationship between the customer and the enterprise to improve the digital customer experience and digital operational excellence. The digital customer experience architect roles develop architecture strategy for a customer lifecycle, collaborate on digital product and service design, and guide customer technology choice. The digital operational excellence roles guide integration with ecosystem partners, support innovation with technology, and co-develop agility strategy. Visual of digital customer experience architect developing, collaborating, and guiding customer with a digital customer experience. Enterprise sources, delivers, and digitizes with digital operational excellence by the digital operational excellence architect. Figure 10:40 the relationship between the customer and the enterprise can improve the digital customer experience and digital operational excellence. Attribution, copyright Rice University, OpenStax, under CC by 40 license. This leads to the creation of enterprise reference architectures and specific business and technical architecture blueprints that represent the various views of architecture within the business, application, information, and technology domains. The scope of these views may then be refined to drill down into specific business units, portfolio, and project-level architectures. Within each level of scope, it is possible to apply architectural styles and corresponding implementation styles available within a pattern catalog. As we have learned, patterns can be applied to project-level architectures as part of high-level design and via leveraging of the architecture management umbrella activity. Architectural and implementation styles may be reflected within blueprints. For example, Figure 10:41 represents how a conceptual technical architecture blueprint leverages the business process management (BPM) architectural style. The diagram answers 6 questions. Who is initiating the business event? What is the classification of the business event type? What channels are provided to initiate the business event? What is the method used to digitize recognized business events? How are business events digitally managed during their life cycle? What automation, organizations, and processes are needed to support digital business event management? Blueprint displaying a business process management model. Figure 10:41, a conceptual technical architecture blueprint leverages the business process management (BPM) architectural style. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Figure 10:42 illustrates a technical implementation architecture blueprint that leverages specific implementation styles, and Figure 10:43 illustrates the same along with callouts identifying specific products and related vendors selected to implement and deploy the solution. Illustration of a technical architecture blueprint. Figure 10:42 a technical implementation architecture blueprint leverages specific implementation styles. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Illustration of technical implementation architecture blueprint with various callouts indicating products and vendors. Figure 10:43 technical implementation architecture blueprint shown earlier with callouts specifying products and related vendors selected to implement and deploy the solution. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Human-centered computing architectures and related patterns. Human-centered computing, HCC, is a newer term that subsumes human-computer interaction, HCI, and includes social computing and HCI. HCC studies the design, development, and deployment of mixed-initiative human-computer systems. HCC-HCI is a subfield within computer science that is concerned with the study of interaction between people and computers. The main objective of HCC-HCI is to make computer systems more user-friendly and more usable. HCI studies the design, evaluation, and implementation of user interfaces for computer systems that are receptive to the user's needs and habits. It is a multidisciplinary field which incorporates computer science, behavioral sciences, and design. The field of computing basically seeks to provide a framework for the integration of human sciences and computer science in a manner that promotes the progress of human activities. With this respect, human-centered computing models design computing systems that support and enrich human existence. Users interact with computer systems through a user interface, which consists of hardware and software that provides means of input, allowing users to manipulate the system, and output, allowing the system to provide information to the user. The design, implementation, and evaluation of interfaces is, therefore, a central focus of HCC-HCI. Corresponding process patterns are applied when designing HCC-HCI architectures. Pattern-based frameworks may be used to study, analyze, and translate the interactions of people with their surroundings into collaborative solution architectures, cloud-based architectures, and related patterns. Big clouds, e.g., Amazon AWS, Google Cloud Platform, IBM Cloud, Microsoft Azure, are available today to help put together complex solutions in an enterprise context by providing platform as a service (PaaS) capabilities that can be assembled very quickly. For example, the cloud-based implementation architecture shown in Figure 10.44 uses three different clouds: social media cloud for data collection, private cloud for predictive analysis, and public cloud for data mining. These clouds collaborate in a mashup configuration and provide a cost-effective way to devise and implement solution architectures that leverage data collection, secure data mining, and intelligent analytics patterns. Scalable data processing framework implementations, e.g., Hadoop, Spark, are also readily available on the big clouds to provide efficient means of handling large amounts of data. Illustration of public users and internal user interacting with a social media cloud, security, data processing, data collection, a data mining backup storage cloud, and a decision-making GUI statistics cloud. Figure 10.44 three different clouds that include a social media cloud for data collection, private cloud for predictive analysis, and public cloud for data mining are collaborating in a mashup configuration. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Microservices architectures and related patterns. A microservices architecture, called a microservice, is an approach to building a software solution as a set of small services, i.e., independent parts that may be deployed locally or on the cloud. The cloud holds data, software, and services that run on the internet instead of on a local computer. While microservices architectures are mainly oriented toward providing backend services, the approach is also being used to enable solutions, front ends. Each service runs in its own process and communicates with other processes using protocols such as HTTP, HTTPS, WebSockets, or AMPQ. Each microservice implements a specific business capability within a certain context boundary, and each must be developed autonomously and be deployable independently. Finally, each microservice should own its related domain data model and domain logic, and could be based on different data storage technologies such as SQL or NoSQL, and different programming languages. Figure 10.45 illustrates many patterns associated with microservices architectures such as motivating patterns and solution patterns. Multiple service hosts, database per service, access token, and health check API are examples of microservices. At a high level, microservices provide long-term agility and enable better maintainability in complex, large, and highly scalable systems by making it possible to create applications based on many independently deployable services that each have granular and autonomous life cycles. Illustration of microservice architecture linking to testing, observability, UI security, discovery, style, communication, data deployment. Figure 10.45 multiple service host, database per service, access token, and health check API are examples of microservices. Data source, C. Richardson, microservice architecture pattern, HTTPS. Microservices, EO/patterns/microservices, HTML, attribution, copyright Rice University, OpenStax under CC BY 40 license. As an additional benefit, microservices can scale out independently. Instead of having single monolithic applications that must be scaled out as units, specific microservices may be scaled instead. This enables scaling just the functional area that needs more processing power or network bandwidth to support demand, rather than scaling out other areas of the application that do not need to be scaled, which results in cost savings because less hardware is required. Learning objectives. By the end of this section, you will be able to identify software engineering process patterns, describe the progression from software models to software implementation, the process of managing, designing, and describing the solution engineering in relation to specific business problems is called solution architecture management. A solutions architect manager is responsible for building teams, establishing relationships, setting strategy, and measuring and delivering results for any problem or opportunity the enterprise may face. Industry Spotlight. Solution Architecture Management. Solution architecture management is important in every industry today. It plays an especially crucial role in the healthcare industry. Solution architecture is used to maintain electronic health records and ensure patient data privacy and security. As healthcare systems become more complex and data becomes more sensitive, solution architecture can be used to engineer secure, scalable, and efficient systems. These frameworks allow providers to access reliable information while maintaining compliance with data regulations. Software engineering process patterns. As we learned in Chapter 9 Software Engineering, the software process can be defined as a collection of patterns that define a set of activities, actions, and tasks required to develop computer software. Software engineering is a detailed study of engineering to design, develop, and maintain software. Software engineering process patterns establish collaborative communication between customers and software engineers to guarantee the successful completion of task patterns within the project requirements and the project scope. As you may recall, various processes and related process patterns were discussed in Chapter 9 Software Engineering to explain how software solutions may be developed by refining an architecture model into a fully coded, ready-to-deploy solution. Technology in everyday life. Architecture management in real life. Solution architecture management may not directly impact individuals in their everyday lives, but it indirectly influences their experiences through the development and management of various technological solutions. It ensures that systems like banking apps, online shopping platforms, and smart home devices function efficiently by managing how the different components of technology work together. When well implemented, it improves the reliability and performance of these tools, making daily tasks more seamless. Link to learning. To learn more about enterprise architecture and how it is used in modern business and tech, explore the websites of industry publications like CIO Magazine for current insights and trends in technology management. From software models to software implementation, recall that a subsystem is a set of collaborating components that perform a given task included in software systems. It is considered a separate entity within a software architecture. A component is an encapsulated part of a software system, which has an interface and serves as a building block for the structure of a subsystem. Subsystems interact with other subsystems and components to perform their designated tasks. At a programming language level, components may be represented as modules, classes, objects, or as a set of related functions. When designing architectures for software systems, software designers typically start with a requirements model, either explicit or implied, that presents an abstract representation of the system. The requirements model is a model that describes the problem set, establishes the context, and identifies the system of forces that hold sway, such as design quality attributes. The method of hiding background details, i.e., unnecessary implementation, about the data so that users only see the required information is called abstract representation. In a traditional architecture design approach that does not leverage patterns, software designers gather the big picture from the requirements model and proceed with defining external entities such as other systems, devices, and people. The software system interacts with the external entities and defines the nature of the interaction. Software designers then need to identify a set of architectural archetypes and specify the structure of the system by defining and refining software components that implement each archetype. An archetype is an abstraction, similar to a class, that represents one element of system behavior. Think it through. Architecture and software engineering. Architecture activities and software engineering activities collaborate throughout the software development process. The architecture provides the blueprint for software engineers to follow, while software engineering activities provide feedback that helps architectural decisions. Given the fact that architecture is maintained at various levels of scope within the enterprise, how do architecture activities integrate with software engineering activities? Figure 10:46 illustrates how enterprise architecture management activities typically integrate with the solution development lifecycle within enterprises. The integration of enterprise architecture management activities with the solution development life cycle ensures that solutions are developed in alignment with the organization's strategic objectives, architectural principles, and governance requirements. It helps optimize resource allocation, streamline development efforts, enhance interoperability, and improve the overall effectiveness of technology solutions within the enterprise. Chart of steps and who implements them. Get project solution development lifecycle, plan, needs, software testing, EAMF design perspectives, architecture design tools and technology services development tools. Figure 10. 46. This illustrates how enterprise architecture management activities typically integrate with the solution development lifecycle within enterprises. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Architectural and design patterns. Design patterns are a representation of the previous test solutions to a specific problem, which is useful for solving future problems. When software designers think about applying patterns or start thinking in patterns, they first try to relate patterns to the requirements model, which communicates the big picture and the context in which the software to be built resides. After that, they extract the patterns that are present at that level of abstraction and begin their design with big picture patterns that set a context or skeleton for further design work. They then work inward from the context, looking for patterns at lower levels of specialization that contribute to the design solution. The same steps of applying patterns are repeated until the complete design is fleshed out, and the design is refined by adapting each pattern to the specifics of the software being built. For the approach, the various patterns mentioned earlier are applied to the big picture with their level of abstraction in mind. Remember that an architectural style is a set of characteristics that make a software system notable or identifiable. It is also a transformation that is imposed on the design of the entire software system. In any software system, there is a set of architectural constraints that restrict the roles features of architectural elements. An architectural style corresponds to coordinated roles and allows relationships among the elements within any architecture that conforms to that style. An architectural pattern expresses a fundamental structural organization schema for the software system by predefining the subsystem's responsibilities, creating rules and guidelines for organizing the subsystems, and building relationships between subsystems. Finally, refining the subsystems or components of the software system, or the relationships between them, is the rule of a design pattern. This provides a scheme that describes a commonly recurring structure of communicating components and solves a general design problem within the particular context of the software system. When delving into the architectural design of a software system, it typically becomes clear that the system cannot be designed outright by just applying patterns. Thinking in patterns does help relate patterns to a technology environment requirement model and typically reveals that software solutions should leverage characteristics from several architectural styles, e.g., cloud, P2P, and microservices. It may also help identify the need to leverage the EAM, BPM, and intelligent autonomous agents architectural patterns as part of a software solution. Concepts in practice. Enterprise architecture and land development. It is easy to think about a land development project as being focused on developing a number of home communities populated with custom homes. The land development company can be considered at the enterprise level. Each individual home community is developed by business units within the enterprise, and individual homes within each home community are created as individual projects. This can be compared to what is happening as enterprise architecture is applied to manage enterprise, portfolio, and project-level architectures. At the project level, managing software projects becomes the concern of the software engineer, but it is clear that enterprise architecture is required to ensure that the individual projects are implemented to follow the guidelines established at a higher level. Enterprise technical architecture frameworks. While the architectural design approach leads the way to pattern-based design, patterns themselves may not always be sufficient to develop a complete design. In some cases, it may be necessary to provide a framework. Remember that a framework is an implementation-specific skeletal subsystem for design work. Mini-architecture provides the generic structure and behavior for a family of software abstractions. Memes, i.e., metaphors, specify the subsystem's collaboration within a given domain. You can reuse the mini-architectures along with a meme to create the framework, which is not an architectural pattern, but rather a skeleton with a collection of plug points that enable the framework to be adapted to a specific problem domain. The plug points, also called hooks and slots, enable you to integrate problem-specific classes or functionality within the skeleton. Therefore, a framework defines the architecture of a family of subsystems, provides the basic building blocks to create them, and defines where adaptations for specific functionality should be made. In general, patterns can be used to describe the framework as information about the system, and the frameworks are software that defines a generic design. Software stacks. A software stack is a collection of independent components or subsystems, such as operating systems, protocols, databases, architectural layers, and function calls that work together to support the execution of an application. As architectural models are being transitioned into implementation architectures, it is necessary to identify specific products that may be used as part of the implementation. This is where the selection of product software stacks takes place. For example, a choice may be to select among IBM, Oracle, or Microsoft product stacks such as Dynamic 365, or a combination to implement a particular architecture. Figure 1047 is an example of a simple software stack for a website implementation. The stack consists of a user interface, application layer, application infrastructure, and tech infrastructure. Icons of user interface: Chrome, Firefox; application layer: Python Bootstrap; application infrastructure: Django, MySQL; tech infrastructure: Linux Server. Figure 1047. The stack consists of a user interface, application layer, application infrastructure, and tech infrastructure. Attribution: copyright Rice University, OpenStax, under CC by 4.0 license. Once a software stack is selected, various products can be added via callouts on the corresponding implementation architecture blueprint. Global issues in technology. Security of architecture management around the globe. Global issues in technology can have significant implications for solution architecture management worldwide. Solution architecture management needs to address data protection regulations, ensure secure handling of sensitive data, and implement robust security measures to safeguard against cyber threats. Complying with the European Union's GDPR requires organizations to implement strict data privacy controls. This, in turn, influences the design of global IT solutions, as they must account for local and regional regulations. Implementation patterns and idioms. As we discussed before, design patterns address general structural principles. In contrast, idioms represent low-level patterns that describe how to solve implementation-specific problems in a programming language, such as managing memory in C++ or Java. As architectural models get transitioned into implementation architectures, it becomes necessary to specify how architectural and design patterns are realized practically within the solution. This mapping actually starts at a high level with the architectural styles themselves. For example, a BPM architectural style may be realized via the selection of an enterprise REST services and with a corresponding product such as MuleSoft. This subsequently dictates the use of specific implementation patterns and idioms specific to the MuleSoft product stack.